Welcome back to our series on applied regression analysis. I'm Mark Ledbetter. This is lecture video 33, part A. We are in chapter 9, finishing that up with part 5. And so we've looked at multiple partial f-tests, and we've looked at strategies for variables added last, variables added first, or in order, I'm sorry. So we looked at those strategies last time, and now we're going to look at tests involving the intercept and some other tests and methods for multiple regression. All right, so we may want to test whether the intercept is significant or not, 0 or not, and it's usually performed with an intercept added last test. So this is, two models are compared, the full model with the intercept in it, and then the full model without the intercept, okay, with the intercept removed. And the null hypothesis is that beta naught is equal to 0 versus HA beta naught not equal to 0. And so the test statistic is SSE without beta naught minus the SSE with beta naught divided by SSE with beta naught over its degrees of freedom. And so this will be an F statistic with 1 degree of freedom in the numerator, n minus k minus 1 in the denominator. So let's look at our data from last time, and unfortunately I only included this table. I didn't include the second table for the second test, so we'll just have to refer back to that table. And in fact, though, I might be able to pull that up for us. So let's see if I can pull that up from last time. And 32, and here we go. Okay, so we have both these tables. All right, great. So we'll be able to refer back to it. Okay, so the first thing we want to do is the equivalent t-test in the let's see, so it says the equivalent t-test in the SAS output in our example, the SAS output. Our example t-statistic is 3151, so let's find that, and so here is 3151 for the intercept, okay, and the p-value is less than 0.0001. Now, for the F statistic that we're talking about, we take the SSE without the intercept, and that in the full model, that's here, and that's this one, and we subtract the SSE with beta naught in the full model down here, and that's this. And so we subtract that, and then remember that this is really an MSE, so we divide by 1, but that gives you the same thing. And then we take this and divide by its degrees of freedom, which is going to be 8 in this case. We see 8 with the full model. All right. And this gives us 992.88, which is a very huge F value. If we take the square root of that, then we get the 3151, which was our T statistic, the equivalent T statistic. Now, an intercept added, so that's one method. The next method is an intercept added last test, can be done as well, and this is actually added first. So that was added last, this is added first. So we have y equals epsilon and y equals beta plus epsilon. So we have nothing in the model, and then we have just the intercept. So this reduces to n, we can write it ny bar squared over SSY over n minus 1. But we can use this F statistic up here that we have, and that was going to be SSE 6, that is without the beta. So let's switch over to here, and so we see 6 is here, and then, okay, so then we have, yes, and then we have 7. So we have, here's 6, here's 7. So let's look at 6 and then 7. So we have, here's 6 with nothing in it except the error. And I'm making this messier than it should be. So here we have that. And then here we have with just the beta, and this is variables added in order, not variables added last. So that was a typo. And so we take those, we subtract, and then we divide by the degrees of freedom, which is 11. So we have 888 divided by 11 degrees of freedom in this case. That's the total, all right? Without 7 is without anything except the intercept in it. So that would be the same as here. And so we take 888 divided by 11, and that gives us 584.14. That is a huge F value. And we have, let's see, 1 and 11 degrees of freedom. So that's going to be highly significant. And they didn't give us the p-values here, but that's okay, we know it. So alternately, we can use SSE from the largest model to better estimate sigma squared. If you're interested in that, see page 81 in the book. And so this is not added last, this is added in order. That's the test that we did here. Okay, so let's look at problem 1. This is problem 1 in chapter 8, and we're going to use that information to answer these questions. So part A is conduct overall F test for the significant regression for 3 models. Be sure to state the null hypothesis, the alternative hypothesis for each test, and interpret the result. And I will say, I would add, instead of just interpreting the result, I will want formal conclusion statements like I gave you in previous lessons, or videos. So we'll make sure that we point those out. So for the model with just x1 in it, age, we're going to write the null and the alternative, beta 1 equals 0 versus beta 1 not equal to 0. The F statistic here, we find that 45, it's right here, and so this is the model with just age in it, and the p-value is given here, and we have 1 and 30 degrees of freedom. And so I have to get to the right one. So 1 and 30 degrees of freedom, p-value here. We would reject H naught, and so there does exist sufficient evidence to conclude that age is linearly associated with systolic blood pressure and aids in the prediction of systolic blood pressure at a 95% confidence level using a simple random sample of n equals 32, because this is n minus 1. Okay, so that's what I'm looking for in your analysis in any thing that you submit. All right, so for the model, now, for the model with age and smoking, to predict systolic blood pressure, we now have this, and I don't like how they write this. This would be at least 1 beta I equals 0, I equals 1 and 2. Okay, that's a better way to writing that. So we look down through here and we find the model that they've given us with age and smoking, and here's the F value, here's the P value, and 2 and 29 are going to be our degrees of freedom, which we see here. And so we definitely reject the null hypothesis. So we know that either beta 1 and or beta 2, just from looking at that, we'd know that at least one of them was significant. Now, if we have the t values down here, we can look at that and we can see that age is highly significant here, and smoking, but QIT is borderline. Okay, and so so we can tell more than what we've said here by looking at those t statistics. Now, in the model with all 3 variables, where x3 is QIT, we write h naught beta 1 equals beta 2 equals beta 3 equals 0 versus, and again, at least 1 beta I not equal to 0, I equals 1, 2, or 3. Okay? And here we have an F statistic of 29.71. We have 3 degrees of freedom in the numerator, 28 in the denominator, and a p-value less than 0.0001. And again, we would reject the null hypothesis. Okay, so and we know that some combination of those 3 predictors is very significant in predicting this systolic blood pressure. Okay, so based on the results in Part A, which of the three models is best? Well, this is a very difficult question to answer with the information they've given us. In fact, they don't even really answer it. They just say, so they do. They say smoking and age was selected as the best model based on R-squared values. So they didn't give us the R-squared values in this. So we could calculate it now if we remember our formula that you can use. But what I would do is I would look at this and say, in this model, these two are highly significant. And this is borderline. And do you really want to increase the complexity of your interpretation and your analyses by adding another variable when it's kind of borderline? And this is not the best way to decide. The best way to decide is to use an adjusted R-squared value or some other test, likelihood ratio test that we'll talk about later on, I believe. Okay. So it makes it very difficult. Without having more information, it is difficult to decide which one's best. And as they said, a variable's added last or a test or the other model selection strategies, those can help us decide which model is best in that for predicting. You know, that balance of highly significant versus parsimony, not as many, as few predictors as possible, and get as much predictive ability as possible. Okay. So an experiment was conducted regarding quantitative analysis of factors found in HDL, high-density lipoprotein, in a sample of human blood serum. There's three variables that they think are highly predictive or could be associated with HDL, which HDL is the Y, total cholesterol, total triglycerides, and this sinking pre-beta or SPB, coded as 0 if absent, 1 if present. Okay, so there's the data. Now, we want to test whether X1, X2, or X3 alone significantly helps to predict Y. So we're going to, we can use, this is SS type 1 SS, so that means that this one is just X1 alone. And so we can use that. So we can use our 46.24 basically, so that should be a 4, over how we get this number here is we take 4613.62, that's right here, and we subtract this 46.24 from it. And that will give us this value here. And then we divide by the 40 degrees of freedom, because it's we have 1 in the, this is really divided by 1 in the numerator, so 40 in the denominator. And when we look up this 0.41, let's look that up in the F table. The 0.25 here in the upper tail is the best we can do. And so 1 and 40, here it is, it's a 1.36, and a 0.41 is smaller than that. So we know that the p-value is at least 0.25, okay, at least. So let me clear that. So it's, yes, okay. So it's not significant. We would fail to reject the null hypothesis. There does not exist sufficient evidence to support the claim that beta 1 is not equal to 0 at a 95% confidence level using a simple random sample of n equals 42. One more than that, all right? Okay, the second test for beta 2 equals 0. Now they've given us this because here, these are type 1 SS, so this is really X2 given X1 at that point. And this would be X3 given X1 and X2. So we can't use those. We have to have another model. And here we have an F value of 0.19 and 1 degree of freedom. And again, we'll have 40 in the denominator. And the p-value they give us is, it's here, is 0.6687. We do not reject the null hypothesis, so we conclude we don't conclude. We fail to reject the null, and so there does not exist sufficient evidence to support the claim that beta 2 is not equal to 0 at a 95% confidence level. All right, using a simple random sample of n equals 42. So just remember, I'm just going to keep on telling you what I need you to put in the answers. All right. So now the third test, beta 3 equals 0 versus beta 3 not equals to 0. Here's the model with just x3 in it. And again, they've given us the printout here for the source. 7.58.0088 is our p-value. That is less than 0.05. We do reject h naught, so beta 3 is significant alone. So we have, we do not reject in the first, we do not reject in the second, so we do reject in the third. All right. Now, we want to test whether x1, x2, x3 taken together helps to significantly predict y. So our null hypothesis, beta 1, beta 2, beta 3 are equal and equal to 0. And again, this would be better written as at least 1, it's supposed to be a 1, beta I not equal to 0, I equals 1, 2, or 3. Okay, and in this model, there. So our F statistic is going to be SS of x3 given x2, x1 plus SS x2, given x1 plus SS x1. And there's 3 of them, so divided by 3 degrees of freedom over the MSE with the full model. Okay, and so the MSE with the full model, they've calculated it here, but I think we could just take 114 here, and so I don't have my calculator to see if that's the same thing. So we've taken 46.24, that's here, and then 89.15, and then 684.37. We've added those, and we've divided by, okay, so it's 38, so we can't use that value. That's why we had to do it on our own. Okay, so, yeah, that's right, because we have 3 up here. We have 3 of these. 3 from 41 is 38. So we take the 4613, the total, SSY, and subtract all 3 of these from that, and then divide that by 38. And we get a 2.74 for our F statistic. It has 3 and 38 degrees of value, 3 and 38 degrees of freedom. So let's take that and look it up. So they're saying that's between 0.05 and 0.10. How did they get that? Using the table. So 3 and 38. So I look at 3, and I go down to 38, and I do have that here. So 3 is the third one over 38. So that's a 1.43 here, and 1.43, and we're at that's too low. We're higher than that. So we need to go to another table. So we'll go to the one that has 0.1 as the p-value, so upper 10%, and 3 and 38. 38 is going to be 2.23. So I believe our value is still larger than that. So 2.74, and that is 2.23. So we're larger than this. Now let's look at 0.05, and there's 0.05, whoops, 0.05, and again 3 and 38, and this value is 2.85, so it's smaller. Our value is between 2.85 and 2.23, so that means the p-value is between 0.05 and, whoops, just locked it up. And up here, 0.10. So it's between 0.10 and 0.05 because our value is in between those two critical values. Okay? So that's how we get that p-value, and that's the best we can do using a table. That's the best we can do. But we know it's greater than 0.05. So at 0.05, we would not reject the null. I would caution you in real life to be careful with something that's between 0.05 and 0.10. There is an association there. So, or there's potentially an association there. So be careful in just discarding that, okay? So here is the conclusion that I would have you write. So please make sure that you look at this. This is what I would like, okay? And now, the third test, whether the true coefficients of the product terms x1, x3, and x2, x3 are simultaneously 0 in the model containing x1, x2, and x3, plus these product terms. So specify the two models being compared, state the null hypothesis in terms of the regression coefficients. If the test is not rejected, what can you conclude about the relationship of y to x1 and x2 and x3 when x3 equals 1, okay? So we're looking at the relationship of y to x1 and x2 when x3 is equal to 1, compared to the same relationship when x3 is equal to 0. All right. So in the full model, this is our answer. Here's our full model with all of these terms in there, all three variables and the two interaction terms here, or products. And the reduced model is going to be without these two circled things in there. So without the two products. And so, so we've got a little run-on going here. The null hypothesis is that beta 4 and beta 5 is equal to 0 versus that at least one of them is not in the model, the full model. So the F statistic here is given as x1, x3, x2, x3, given x1, x2, and x3. So we need to have SS of x1, x3 given x1, 2, and 3 plus SS of x2 given x1, x2, and x1, x2, x3, and that. So we're using the variables added in order, type 1 sum of squares, and there's two of them, so divided by 2, divided by the MSE with all of them in there. So we look over here and we see that we have 48 and 26. We take and add those, okay, together and divide that by 2 in the numerator. And then we take the full sum of squares for y, 46, 13, and we, I don't know, sorry about that. Didn't mean to do that. And then we subtract these same values. We subtract those values and we subtract the values for x1, x2, and x3 here. So we actually subtract all of these values from it because we want the model with all of them in there. Okay, so we subtract that and we divide that by 36. And let's see, because we've got 1, 2, 3, 4, 5, and from 41. So 41 minus 5 equals 36. So that's where we got the 36. We do that and we get a 0.36. And at 2 and 36, the p-value is greater than 0.25. 2 and 36, 0.36. So 2 and then 36. So 2 is the second one. 36 is here. 3.26. Oops. And this is 0.36, which is smaller than 3.26, way smaller. So we know that the p-value is much higher than 0.25. I might clear that out again for next time. We'll come back. And now we're looking at a test for whether x3 is associated with y after taking into account the combined contribution of x1 and x2. What does your result, together with your answer in part C, tell you about the relationship of y with x1 and x2 when SPB is present compared to the same relationship when it's not? And so I think I skipped this. I'm sorry. So we have the p-value for this one, greater than 0.25. There does not exist sufficient evidence to support the claim that beta 4 or beta 5 is not equal to 0 and 95% confidence level tested on a simple random sample. And we should say in the model. So I'm sorry I forgot. In the model, put the model. Okay. We may infer that the relationship of y to x1 and x2 does not change when the value of x3 changes because these are not significant. So, but we'll see in Chapter 12 that this implies that the regression surfaces relating y to x1 and x2 are parallel for both values of SPP. Okay. Actually, it's supposed to be SPB, so that's a typo. SPB. Sticky something, proto something, beta, pre-beta or something. Okay. So now we're doing this test for whether x1, x3 is associated with y after taking into account the combined contribution of x1 and x2. This with part C, what does that tell us about the relationship of x2, x3 when SPB is present compared to the same relationship when it's not? So our null hypothesis and our alternative hypothesis in the model, and we have f of x3 given x1 and x2, that's SS of x3, x1, x2 over 1, and then the MSE of x1, x2, x3. So we come over here and we look at x3 given x1 and x2, because it's type 1 SS, 684, and then we take the total, 4613, and we subtract these three from it, okay? So all three of those, and that's 3 from 41, that's 38, and degrees of freedom. And so we have 1 and 38, and again we end up with a 6.85, and that is between 0.01 and 0.025. So that is less than 0.05, and I'll let you look that up in the table this time. And again, I need in the model, and please include the model. Okay, we always include the model. Sorry, I forgot that. So there does exist sufficient evidence. All right, together with the results of C, this implies that the regression surfaces of y1 relate y to x1 and x2 are parallel, but not coincident for both values of SPP. That is, the surfaces have different intercepts for the two values of SPB, not BP. Okay, so I've reversed those. Those are PB. All right. And so what overall conclusion can you draw about the association of y with the three independent variables for this data set? X3 is associated with y, but the other two independent variables are not and should not be included in the model. Okay. So I hope that has helped you figure out how we can do some additional tests and using these variables added last and added in order methods. So please don't forget to scan your lecture notes by midnight, the date listed in the course calendar. If you have questions, please come to virtual office hours. I'm happy to help you. If you can't do that, email me both a picture of the problem and your work so far, and I will try to help you through email the best I can. So please take care of yourself, and we will see you next time.